Hello, I'm Bruno Zumbo. I'm professor and distinguished university scholar at the University of British Columbia. And this is the first of a series of UBC Paragon webinars. This is UBC Paragon Webinar Series 2021-1. Today I want to talk to you about a pervasive problem in psychometrics and a solution that my program of research offers, and give you sort of some overall insight into the issues. The title of this presentation, it's a long title, it's called Embedding IRT in Structural Equation Models as a Solution to Problems with Measurement Error and Predictor Variables in Validation Research. It's important to acknowledge that first and foremost, some contributions by my collaborators, Professor Roland Thomas and Dr. Irene Liu at Carleton University in the Sprott School of Business. This presentation is an integration and extension of my program of research on item response theory, on IRT, test scoring, and validation methods and variable ordering. Here's an outline. I have four broad sections I want to cover. Some opening remarks, motivating the problem itself, giving you some context for it. I'd like to discuss three solutions that are described. One is using the observed total score. The other is using predicted latent variable scores. And there's actually three approaches to that: the likelihood, the posterior distribution-based approaches, and plausible values through multiple imputation. And the third is the solution that I want to speak most about, which is embedding our IRT in structural equation modeling. Try and give you an example of this, including an issue of variable ordering, which through the latent variable Pratt index, and then some conclusions towards the end. So a very common research question in assessment and validation studies use regression, and these kind of questions include which of the variables is most predictive of a criterion variable. So think if we're doing some sort of criterion validation study, we have a series of predictor variables, and we ask the questions, which of the variables is most predictive, and what variables what variable or variables is most explanatory of our test scores. In a sense, these are highly interrelated types of problems. In fact, if one can think of them as the same mathematical problem cast two different ways. Let's consider an example to motivate our discussion of a validation study investigating predictors of a test of knowledge of numbers, sort of a grade 8 mathematics test. So the question here is, let's look at the predictors of a test of knowledge of numbers from a grade 8 mathematics test. So the criterion is number knowledge. There are 9 test items on it. The predictors of this, because we're trying to understand or either find predictors of or get an explanation, understanding of the sort of variation in number knowledge. The predictors might be availability of computers, time spent on a math homework, tutoring or extra lessons, number of books at home, all of which are observed variables, and a test of how much the students value the importance of mathematics. So it's the students' value of the importance of mathematics. That's really the interesting predictor there. So you have availability of computers, time spent on a math homework, overall, tutoring or extra lessons, the number of books, and all of these 1 through 4 are all observed variables, and a latent variable, which is a measure of the students' value of the importance of mathematics, how much they believe in their value of it itself. The Y variable, the criterion is number knowledge, measured with a 9-item test. There are 3 strategies that are typically discussed in the literature. So you imagine a regression in which Y is the score. If we go back one slide here, the Y, where your criterion and Y variable, which is regressed upon the predictors in a regression kind of model, conventional regression kind of model. It involves some function of or some characterization of these 9 items of an number knowledge. And so your Y variable itself actually has a measurement error in it. Curious enough, so does in number 5, which is the students' values, their valuing of the importance of mathematics, also in this case here. So you actually have a fascinating case where, and typically what they would do, a very typical way, is to compute the observed total score. For example, the number correct score on a math test and a scale score on the value of the importance of math. And then you fit a regression equation and test model parameters using the observed total scores in place of the discrete test items. So it's very common here. You have a case like this. You would just sort of create what would be called the number correct score here, which is you score all the items right, wrong, and then you add them up. And then here you would actually have like a scale score on the test itself, which again is also a observed total score. You have this data, then you run a very typical looking regression. That is actually a very common approach. We'll deal with the issues around that in a bit. The second approach that's picked up in some areas of social science research is predicting individual abilities or trait scores, either IRT, theta scores, or factor scores in a factor analysis, on the math test and separately on the valuing math scale. And so then what you would then do is you would fit an external regression. So you would predict, so this was found for some period of time, actually in the 1990s. You'll see some literature in the 1980s. To the 1990s, beginning of 2000, you'll see large data files in which in those data files are the predicted ability or trait scores. So in a math test, you might get the predicted math score from say, for example, in that case, it might come from an IRT model, some family, one of the family of, in this case, let's say the items are all binary. If they were, there'd be some member of a family of sort of logistic models, maybe a 1PL, 2PL, or 3PL model. You might get the predicted theta score. Alternatively, separately, you would then get the items for the valuing math scale, which is more of a psychosocial measure. Same sort of idea. You run in this case, a factor analysis, and you would then save the predicted factor scores, which in a sense are in fact IRT theta scores. They are predicted scores on a latent variable. And there's really 3 ways that this is commonly done that we're at least going to talk about is the likelihood-based approach, the posterior distribution-based approach, and the plausible values multiple imputation, which is not really a prediction like A or B. So plausible values is slightly different, and we're gonna say a few words about that when we get there. So A and B there, 2A is the likelihood-based approach, 2B is the posterior-based approach, posterior distribution-based approach, or the plausible values. Then an IRT, you run an IRT external to the regression, you get the IRT scores, you even get, then you fit a regression equation and test model parameters using the predicted IRT or factor scores in place of the discrete test items. So in the first one, everything is treated, you just simply sum the observed item responses. In the second one, you might get predicted latent variable scores. And the other thing too is I use the term predicted here. I know they'll often use the term estimated, but we're going to talk about that a little bit as we go along. Really, I think most accurately, these are predicted scores. And then the third one is to embed IRT in structure equation modeling. So let's talk about the first case where everything's based on the observed scores, the number correct or the total score. So a very common approach is to treat the test and or scale scores as observed score composites and use the score composite of variables in the analysis. I've already talked about this. And you would then run sort of an ordinary least squares regression, and measurement error in the criterion can perhaps be thought as to be absorbed in the error term, right? The criterion, the Y variable, which in this case would be the number test score. However, measurement in the predictors is not accommodated for, can be quite problematic. In fact, estimating regression coefficients are biased even as the sample size approaches infinity. this is some results that can be found in the math stat literature, using Cochran, Fuller, Brunner, and Austin in 2009, and others. So these estimated regression coefficients are biased even as the sample size approaches infinity. Also, if you're using some kind of confidence intervals, or you're looking at a test of hypotheses of the parameters, the type 1 error rates can be seriously inflated. So as a sort of side note, far less widely known is the type 1 error rate not only is inflated, but can actually approach 1.0. Let's say you have a nominal nominal error rate of 0.5. Doesn't really matter much. The actual, depending on the correlation among the predictors and the measurement errors, you can get actually inflation of type 1 error rates that are it's approaching 1, which is of course ridiculously low. I mean, that's outrageous. We actually show some of this in a paper by Ben Shear and I in 2013 in the journal Education and Psychological Measurement. But it's a very, so there's a lot of problems with just using the observed total scores. Well, the other approach is to sort of predict individual ability or trait scores. And IRT is used externally to the regression model as a way of getting predicted theta scores, these theta hats, to then input in the regression. Or if continuous item scores, one could use linear factor analysis as well. So you either using, so you could have perhaps continuous item responses, you might have polytomous item responses in a sort of self-report measure, and then might have binary items in it. And so you're looking at really IRT and or linear factor analysis or factor analysis kind of approaches. You get a predicted score that's done externally, and then those are entered as input into a regression equation. Two broad ways of doing this, the two types of methods of predicting ability, that is obtaining this theta. One is this likelihood-based approach, and is the posterior distribution-based approach. It'll be assumed that items, when doing this, it'll be assumed that items and the parameters of the ability distribution are not known exactly. In practice, of course, item parameters will be replaced by their consistent estimates, which in current practice is quite often seen in current practice in item response theory. So in practice, these item parameters, you'll get the item parameters. The IRT is often done in this sort of implicit two-step approach where we'll get item parameters. There's a variety of ways to separate address. I'm glad to give a talk on that separately. Get item parameters, and then from there you'll get predicted theta scores or latent variable scores. In practice, item parameters were replaced by their consistent estimates. By consistent, I'm using that in a technical sense, a statistical sense. That's often the case. And then you're going to use maybe a Bayesian approach, maybe a likelihood approach to get your predicted theta scores. The likelihood-based approach is very common. What I'm calling the posterior distribution-based approach is aligned with sort of Bayes estimates of these. There's also plausible values, multiple imputations. This is a little different because in this approach, as I hinted at earlier, you're not really predicting thetas. You treat abilities and the ability scores, the thetas and latent variables, as missing. You then use random draws from a predictive distribution to estimate the regression parameters. Used or was used for the longest time in Statistics Canada for PISA and TIMSS data. This may be a little, things may have changed a little bit at StatsCan, but I think this is very much what they still do. And for multiple imputation in the IRT context, see a lovely paper by Don Rubin in 1987 and a terrific paper by Miss Levy Johnson and Muraki in 1992. Excellent ways of using sort of multiple imputation. In the likelihood-based approach, just digging a little bit deeper, you get these maximum likelihood estimates. It treats the subjects, the student or the survey respondents, it treats their ability as a fixed parameter, theta sub I, and assumes that the subject's score, that is the X outcomes, right, the test outcomes X, is a random draw from population of subjects having that particular ability. So when you're doing these likelihood-based approaches for the MLE, it treats the subject's ability as a fixed parameter, theta sub I, and assumes that the subject score, right, the test outcomes X, is a random draw from a population of subjects having that ability parameter. Then we write the approximate likelihood for the ML estimation in the following manner. Here, you can see this here. It really emerges quite out of some very basic assumptions around things like independence, local independence. The maximization yields the MLE. And so the MLE is a function of the X sub I, which are the item responses. Interesting properties about the MLE is it's asymptotic. You have asymptotic conditional bias. It's at the order big O 1 over N, where N here is the number of items, not sample size, the number of items. The conditional mean square error, the MSE, with error term of order small o 1 over the number of items. And so what becomes important to keep in mind here is that you need a large number of items. People often talk about sample size here in this context, but really it's the number of items that become important. Sample size meaning the number of respondents. If you think of a typical setup of an array, a data matrix where row are people, subjects or test takers or survey respondents, and columns are variables. In this case, they might be item responses or survey responses. Those columns, a column for each of those. It's the number of columns that's important in this case here, at least at this portion of it. Don't forget, we're treating the subject's ability as a fixed parameter, right? And assumes that the subject score, right, these test scores, X, is a random drawn population of subjects having that particular ability. And this is an important component of it. You'll see it described in some outstanding literature by various psychometricians. Paul Holland does a very nice job of it, of course, and others who lay out this sort of characterization of this. The likelihood-based approach, there's also a weighted likelihood estimates, and this is obtained by maximizing the same likelihood multiplied by a function of theta. So it's the same likelihood here, and it has smaller bias properties as the number of items approaches infinity. So as you get this, there's this growth and this increasing rate of increase in the number of items, you have smaller bias properties. You have a smaller conditional bias than the MLE, so in the order of 1 small o over 1 over N rather than big O, but has the same asymptotic conditional MSE. So we're running into the same sort of issues here. Let's turn now to the posterior distribution-based methods. This approach is a little different. Now what you have is you have a posterior distribution of theta, and can be written in this manner here in a very conventional way. Here, so you get the posterior distribution of theta, so it's theta given the realizations of X sub I, the observed scores, and you can see this expression, very standard kind of expression here. You can get the Bayes modal predictor, also known as the maximum a posteriori, or MAP predictor, and it's obtained by maximizing this above posterior distribution for each subject, for each test taker, for each survey respondent. And so you can get, you're really maximizing the posterior distribution. So you get the map, and you get this maximum a posteriori predictor of it, this Bayes modal estimate there, a max being the mode of a distribution. And this very simple sort of analog of this. The conditional bias and unconditional bias is now of order capo 1 over N. Again, remember that's the number of items that becomes relevant here. There's EAP, or what's called the expected a posteriori, which is really the mean of the Bayes posterior distribution, the posterior Bayesian Bayes posterior mean of that distribution. It's a mean of the posterior distribution itself. So the other one was the mode. This is the mean. Sample mean for IID samples, independently distributed samples of the EAP predictor, is an unbiased estimator of the mean of the ability distribution. So we've got some nice property. However, the unconditional variance is less than the unconditional variance of the latent ability distribution. So you actually have this unconditional variance being well, it's being different than the unconditional variance of the latent ability distribution. This holds for the empirical-based predictor for large samples, a potentially troublesome property unless the number of items is, again, sufficiently large. So again, people keep talking about sample size. It's not sample size. It's actually, in this case, the real issue is the number of items, which explains why in some large educational testing programs, there are a large number of items. When you start using some of these approaches with smaller number of items, we have a whole new issue to deal with here. Let me give you a graphical depiction of regression with predicted variables. For example, you can use the EAP prediction of you have these two latent variables here, the IRT model, all right, for item 1 to K, and the IRT model here. And the regression basically looks like this. So that goes into there, and this is the standard kind of a graphical depiction of it there. You have two latent variables, which are specified there. This is really, they're both, you'll see me switching between IRT and factor analysis, and you'll see why in a moment. The way I think about them in this case, and the way we think about them in this case. The problem with predicting the scores, so fundamentally it comes down to this, that the predicted ability scores are susceptible to a number of important sources of error, and a major source of error, which is a function of the number of items in the test or in the measure. And this becomes important. I want to highlight, this was the whole main point of it, is for a test of fixed n, the test of fixed length, the distribution of the predicted values, the scores, does not converge to the distribution of the latent variable as the sample size goes to infinity. And this has been known since at least the mid-60s. Fred Lord in 65, 69, Little and Rubin in 83, and Louis in 84. So you must have the number of items n, for this to hold, that has to go to, in its mathematical properties, also has to go to infinity. Thus, analyses based on predicted values or scores are subject to bias of the resultant regression parameter estimates. This is an important point to keep in mind as people go through with this. Well, there's a different way of doing this then. Let's actually approach it rather than either naively summing the items and just treating the observed scores or getting some predicted latent variable scores. Well, the approach that Roland Thomas, Irene Liu, and I advocated in a paper of ours in the journal Structure Equation Modeling is that one can embed IRT in a structure equation model, in essence, simultaneous estimation without predicting latent variable scores. This, I think, is very important. This is and so rather than saving the predicted factor scores or theta hats, and then doing an external subsequent regression, fit the whole thing simultaneously. So this is a structural equation model on discrete variables. I think this is an important. We actually studied this in our papers in structure equation modeling and papers by Roland and Irene in the same journal, and we see the properties of this. It's incredibly promising. So. Now, there's other challenges that come with this, but it really avoids some of the other issues. Specifically, we have this going on, right? We can see that there is a structural model and a measurement model, fairly straightforward here. You can see the structural sort of regression model here, right? So we have a latent variable regressed onto these. The measurement models here, you have one, in this case, we can look at this one set here, and we can set another measurement error model there. And we can see thresholds, and you can see now simultaneously, one estimates the taus, the lambdas, the betas, the gammas, by optimizing a quadratic discrepancy function in the following way here. You can see generally we can talk about it, write it in this manner here, right? The benefits when obtains consistent estimates of fixed parameters, and there's no prediction of individual scores, right? This is really the main advantage of it. We all recognize this part. This is a regression. But what about this part? Well, this part is, well, really, it's a factor analysis on discrete variables, right? This example here, these are for binary items, right? So you can see these are for binary items here. But it's fairly easy to write it for ordered categorical variables as well. But these are in fact discrete. It's a factor analysis on discrete variables, if you wish, an IRT model. So we can now see it being pushed together and brought together in that manner. But it is true that discrete factor analysis does have a parallel with normal ogive IRT model. There's an equivalency there, if you wish. And so in this approach, when we perform structure equation modeling, we're actually fitting simultaneous an IRT and an SEM model simultaneously. That's what one does in this sense here. That's what we can see here in the setting of it. Irene Liu, these results are really this sort of depiction. My colleague Irene did a beautiful job several years ago trying to take this apart and bringing it into these various sort of applications. Very promising work at all. A couple remarks. In this context, parameter estimation in the discrete structure equation model is equivalent to simultaneous estimation of IRT parameters and the regression parameters. You will get consistent estimators of the structural parameters, Brunner and Armitage in 1995, for a finite number of items. And this approach sidesteps the prediction of the latent variable scores. It also sidesteps treating the observed scores, item responses, just adding them up or averaging them, whether it's a knowledge test or a self-report measure. Very briefly, I'm going to show you a way of ordering predictors to answer those kinds of questions that are fairly common in validation research in terms of looking at the most important variables. And this is an example of embedding IRT in structure equation modeling. I use an example from TIMS, International Educational Assessment work. 2003 data set grade 8 math tests were used as our mathematics achievement measure. A total of 12 booklets were used in the test. That's for the purpose of our demonstration, just for our demonstration. We'll separately deal with the matter elsewhere. We're going to use one booklet in the present study. This is really more for, as I said, this is for demonstration purposes only. And you can see the student's questionnaire was used to obtain students' background variables and some of the surveys, the importance of mathematics. You can see some of these other variables. Total sample size of 682 participants in the USA responding to booklet 8. The number of boys and the number of girls you can see there. Here's what the model conceptually looks like here. You see a regression, criterion or Y variable, which actually is a combination of binary scored items and a politically scored item. So you can get, these are sort of right, wrong kind of items. And this actually, you could have a half point. And here you now see some rectangulars. Here you have observed variables, homework time, computer availability, private tutoring, number of books, and a latent variable predictor, which itself is made up of ordinal variables. And these, of course, are all correlated with each other. So it's a regression. So Y regression regressed on X. The X's are in this case correlated. And it's made up, and the predictions are made up of observed variables, number of books, private tutoring time, computer availability, homework time, and of a latent variable called self-confidence in learning mathematics. I've used it's a rather old version of M+. You can get more efficient approaches right now in M+. You can do it in Levant as well. Key point, of course, here to get the appropriate regression coefficients is using the correct correlation matrix involving binary or ordinal and continuous observed variables. And Ben Mutain and his colleagues have done this early on. Modeling of ordinal and binary responses, as well as observed and latent predictors. You can see this. These were actually all ordered, all ordinal, the homework time, computer availability, private, and this here is all made up of ordinal responses as well for the self-concept in math learning. So we added a latent variable predictor, so in this case, just to demonstrate it, the self-confidence in math. Off we go. We actually ran it, worked very smoothly, a very simple process in things like M+ or Lavant. Simultaneously fits all of these. And look at this. We can now, depricing this, what we call the Pratt index. It's an approach that Roland Thomas and I have done some work on, where you're partitioning the R squared, the resultant R squared from this model, if you wish. So you get a resultant R squared from this regression. What this is, a very complicated looking regression model. And in fact, it's a fairly straightforward linear regression model, given this is a continuous latent variable. So you actually get the beta coefficients, the standardized B weights, the correlation of each of the predictors and Y, and you can compute what is called the Pratt index. I describe it for latent variable models. I think it was first described in 2007. I think it was the first paper to adapt it to these latent variable kind of models in my chapter in the Handbook of Statistics, edited by Rawan Sinhare. And basically what it is what you do is you multiply the standardized B weight times the correlation, and you divide by the R squared of the model. And you can get a Pratt index. This is D sub j for each of the predictors. And because of how the Pratt index, the geometry of the Pratt index, you can actually add up subsets of them. So you can see that these four variables together, the number of books, tutoring hours, availability of computers, homework time, is together it's 0.458, which is of course the remainder of this. This is a proportion of the R squared. And you can even you could order it within. So within these, the number of books is the strongest predictor within the set of observed, if you wish, sociodemographic variables, as opposed to self-confidence in learning math, which is in fact, of all of them, the strongest, most important predictor, accounting for 54.2%, if you wish, or 0.542 of this R squared. So, and of course, one needs to take into account the size, the magnitude of the R squared in making the interpretation. So, so it's 54, if you wish, 54.2% of that R squared is a self-concept psychosocial variable, and you'll see together here time with home, availability of computer, tutoring hours, a number of books. Even within those, together they're 0.458 of this, 45.8% of this, and within that set, number of books is the most important. So you can get predicted latent variable scores, should be used with caution. So those, those predict theta hats and predicted, in discrete cases, you really need large number of items are really needed. There was actually a very nice paper by Thomas and Sear in 2002 that for 20 items is equivalent to an R squared bias of 40%. That's a Statistics Canada study. It's the National Longitudinal Study of Children and Youth. And so, they're looking at, in the EAP, right, that variance in the EAP base estimate, right, for 20 items is equivalent to an R squared bias of 40%. For continuous items, at least at this point in time, the earlier work, there may even be more exciting work that's been done by Scrondo and Lake later, but they conclude that conventional factor score regression performs badly and should definitely be abandoned. So I think we fall very much in that idea. In the discrete case, simultaneous IRT SCM approach may, if you have this, provide an alternative to the plausible values. IRT SCM does not require a large set of conditioning variables, which are needed elsewhere. The sample size requirements may be limiting in some contexts, so be aware of the complexity of your models. And however, using reliable calibrated items with better convergence, even with smaller sample sizes. I mean, that's it's a nice way of saying if you have very, if you wish, well calibrated, well understood items that have been studied independently in other samples, when you actually put them in here, you'll find that in fact the convergence, it gets even better with small sample sizes. It's not too surprising. I mean, your models, in a sense, that if your model is in this neighborhood of correct models, which can be a very tight neighborhood if you want to think of it that way, plausible models. I mean, then if you understand it well, once it's embedded in a structure equation model, you're going to get better convergence even with smaller sample sizes, right? That's a kind of standard result even in linear regression. If your linear regression model is correctly specified, meaning it corresponds in some sense to the population or generating function of the model that produces the data, the observed data, the hypothetical model, you're going to get fit at smaller sample sizes. Thank you very much. I hope you found this a useful seminar, and I look forward to the next set of seminars as we go on, sharing research with you all that's going on as part of the UBC Paragon Webinar series. Thank you.